March 12, 1945. Deep inside the forests of central Germany, hidden beneath layers of camouflage netting and surrounded by armed guards, a machine waits in silence. The location is a vast hangar complex near Friedrichsroda in Thuringia. Outside, the Third Reich is collapsing. Allied armies are advancing from every direction. Cities burn. Rail networks disintegrate. Fuel shortages cripple military operations. The war that Germany once seemed destined to win has become a desperate struggle for survival. Yet inside this hangar, a very different future appears to be taking shape. The aircraft resting on the concrete floor does not resemble anything else flying in the world. It has no propeller. It has no conventional tail. It lacks the familiar fuselage that defines almost every combat aircraft of its era. Instead, it appears as a single continuous wing, smooth and curved, flowing from one tip to the other without interruption. The shape is so unusual that even the mechanics who work around it every day occasionally stop and stare. There is something unsettling about it. Something that feels wrong in the same way a modern jet would have appeared to someone living in the 19th century. It looks less like a machine from 1945 and more like a visitor from another age. This aircraft is the Horten Ho 229, and the men responsible for building it believe they have created something revolutionary. Not merely a faster aircraft, not merely a better aircraft, something far more dangerous. An aircraft that can hide from radar. Today, stealth technology feels familiar. Modern audiences associate it with the angular surfaces of advanced fighters and the dark silhouette of strategic bombers crossing hostile skies unseen. But in 1945, the concept was almost unimaginable. Radar itself remained a relatively young technology. The British chain-home network had played a decisive role during the Battle of Britain, giving defenders precious warning of incoming Luftwaffe raids. Similar radar systems were appearing across the world, transforming air warfare by allowing nations to detect aircraft long before they became visible to the human eye. To military planners, radar seemed almost magical. To the Horten brothers, it appeared vulnerable. They believed that an aircraft could be designed specifically to reduce its radar signature. Not completely invisible, not in the science fiction sense, but difficult enough to detect that enemy defenses might not react until it was too late. If they were correct, the implications were staggering. To understand why Germany became interested in such a radical aircraft, it is necessary to return to the increasingly desperate strategic situation facing the Luftwaffe in late 1943. By that stage of the war, Germany was losing control of its own skies. The Allied bombing campaign had evolved into a relentless machine. Hundreds of heavy bombers crossed Europe daily. Factories, rail junctions, fuel plants, industrial centers. Everything became a target. The bombers no longer traveled alone. Long-range escort fighters now accompanied them deep into German territory, engaging interceptors before they could reach the bomber formations. The balance of power was shifting dramatically. German pilots still fought fiercely, but losses mounted steadily. Every month, the Luftwaffe found itself weaker than the month before. Everyone could see it, including Hermann Göring. Göring responded in the way he often responded to military problems, by demanding something extraordinary. He issued what later became known as the 3x1000 requirement. The aircraft he wanted would carry 1,000 kilograms of bombs, travel 1,000 kilometers, and fly at 1,000 kilometers per hour. Each number sounded ambitious. Together, they sounded impossible. German engineers quickly realized the problem. The jet engines available in 1943 consumed fuel at astonishing rates. Building a fast aircraft was possible. Building a long-range aircraft was possible. Building a heavily armed aircraft was possible. Combining all three characteristics into a single design appeared beyond reach. Every solution generated another problem. More fuel increased weight. More weight required more thrust. More thrust increased fuel consumption. The cycle repeated endlessly. Most conventional designers quietly concluded that the mathematics simply did not work. Two brothers disagreed. Walter and Raymar Horten had spent years pursuing an idea that many aviation experts considered impractical: the flying wing. Since the early 1930s, they had built experimental gliders and aircraft that challenged traditional design principles. While other engineers focused on refining existing layouts, the Hortens questioned the layout itself. Why should an aircraft have a separate fuselage? Why should it need a tail? Why should large portions of the structure contribute nothing to lift? To Raymar Horten, these were not necessities. They were compromises. The ideal aircraft, he argued, would be one enormous wing. Every surface would generate lift. Every kilogram would contribute to performance. Drag would be reduced. Efficiency would increase. Range would improve. And speed would follow naturally. The theory was radical. Yet their experiments suggested it might be correct. Over more than a decade, the brothers accumulated experience that virtually no one else possessed. Aircraft such as the Horten H-2, H-3, H-4, and H-V demonstrated that flying wings could actually work. Pilots flew them successfully. Data accumulated. Problems were solved. Gradually, the concept matured from curiosity into possibility. So when Goring announced the 3 by 1,000 requirement, Walter Horten confidently informed officials that his brother already possessed the answer. Not on paper, not in theory. In practice, the answer was the flying wing. Government officials responded with skepticism. Many engineers considered the idea unrealistic. Yet Germany's strategic situation left little room for caution. The brothers received authorization. Funding followed. Facilities became available. Deadlines were established. And work began at remarkable speed. The aircraft that emerged looked unlike anything produced anywhere in the world. Its central structure used welded steel tubing in a relatively conventional manner. The cockpit, engine mounts, and major internal systems occupied this reinforced center section. Everything else was different. The broad outer wing panels were constructed primarily from wood. Not because the designers preferred wood, because Germany increasingly lacked aluminum. Resource shortages forced creative solutions. Ironically, those limitations helped create one of the aircraft's most fascinating characteristics. The wooden wing sections consisted of thin plywood layers bonded together around a unique internal material, a mixture containing sawdust and charcoal. To most observers, this looked like a practical manufacturing decision. To Raymar Horten, it served another purpose. He believed the charcoal content might absorb portions of incoming radar energy rather than reflecting it back toward the transmitting station. The theory remained largely intuitive. No sophisticated radar testing facilities existed for him to verify the idea. No advanced computer models supported his conclusions. No scientific consensus existed regarding stealth technology. Yet the intuition persisted, and decades later, researchers would discover something remarkable. The intuition was not entirely wrong. Years after the war ended, engineers finally gained the tools necessary to examine the Horten brothers' ideas properly. In 2008, researchers working with Northrop Grumman conducted detailed studies of surviving Ho 229 components using radar analysis equipment far more sophisticated than anything available during the Second World War. What they discovered surprised many aviation historians. The aircraft was not invisible, not even close, but it was significantly less visible than a conventional metal aircraft of similar size. The charcoal-infused wooden structure appeared to absorb a measurable portion of incoming radar energy. Combined with the aircraft's unusual shape, the effect reduced its radar signature considerably. For radar operators using the British chain-home network of the 1940s, the aircraft would likely have appeared much smaller than it actually was. Perhaps not invisible, but confusing. And in air defense, confusion can be almost as dangerous. A radar return mistaken for interference. A contact dismissed as atmospheric noise. A target classified as insignificant. Those few moments of uncertainty can change everything. Raymar Horten had reached a surprisingly modern conclusion decades before the word stealth entered military vocabulary. The shape itself contributed as much to the effect as the materials. Seen from above, the Ho 229 looked almost unreal. Its wingspan measured approximately 14 meters, placing it within the general size category of a fighter aircraft. Yet its geometry made comparison difficult. There was no conventional fuselage dividing the aircraft into recognizable sections. No tail surfaces projecting behind the wing. No stabilizers creating additional radar reflections. Instead, the aircraft resolved into a smooth, sweeping form that appeared almost organic. Many observers later described it as resembling a manta ray. Others compared it to a boomerang. From certain angles, it looked less like an aircraft than a mathematical idea given physical form. The engines were equally unusual. Two Junkers Jumo 004B turbojets were buried within the wing itself. Each engine produced roughly 7 kilonewtons of thrust. Their intakes sat beside the cockpit while the exhaust exited near the trailing edge. This arrangement offered several advantages. The engines remained protected within the structure. The aircraft presented a cleaner aerodynamic profile. And perhaps unintentionally, the layout reduced both thermal and acoustic signatures compared with many contemporary designs. Today, hiding engine emissions is considered a fundamental aspect of stealth engineering. The Horten brothers arrived at a similar configuration through aerodynamic reasoning alone. The aircraft's performance figures bordered on unbelievable for 1945. Fully loaded, the Ho 229 weighed roughly 6,000 kilograms. Despite that weight, testing suggested maximum speeds approaching 977 kilometers per hour. Such performance placed it in an entirely different category from most Allied fighters. Consider the numbers. The legendary Supermarine Spitfire Mk-14, among the fastest piston engine fighters ever built, achieved approximately 721 kilometers per hour. The famous North American P-51D Mustang reached around 703 kilometers per hour. Both aircraft were exceptional. Neither could catch a fully functioning Ho 229. The difference was not marginal. It was enormous. Had the aircraft entered operational service in meaningful numbers, interception would have become a serious challenge. Production moved to the Gotha wagon fabric facility at Gotha. There, the project received an official production designation and plans emerged for a manufacturing run of 40 aircraft. For a brief period, the future appeared surprisingly promising. Prototype work accelerated. Engineers labored day and night. Design revisions continued. Pilots prepared for additional testing. Outside the factory walls, however, reality intruded with increasing force. The war was ending, and it was ending badly for Germany. The V-2 prototype became the first powered Ho 229 to fly. On February 2, 1945, test pilot Erwin Ziller climbed into the cockpit and took the aircraft into the sky. Observers watched with fascination. What they witnessed exceeded expectations. The aircraft accelerated rapidly, handled well, and demonstrated performance that appeared extraordinary even to experienced pilots. Witnesses later recalled how strangely quiet it seemed compared with other jet aircraft. Others focused on its speed. Many described an almost uncanny sensation while watching it pass overhead. The aircraft looked unlike anything they had ever seen, and it moved unlike anything they had ever seen. For a brief moment, it seemed possible that the Horten brothers had succeeded completely. Then disaster struck. During a later phase of testing, one of the engines failed. At low altitude, Ziller attempted to recover. The aircraft descended. Time disappeared. Restart procedures failed. The ground approached rapidly. Moments later, the Ho 229 crashed. Ziller was killed. His death represented a severe blow to the program. Not only had Germany lost an experienced test pilot, but confidence inevitably suffered as well. Yet work did not stop. There was no time to stop. The engineers continued. The war allowed no pauses. Attention shifted toward the V-3 airframe. This aircraft represented the most advanced version constructed to date. Unlike earlier prototypes, it incorporated the complete wing structure, operational systems, and intended combat configuration. By early 1945, it stood largely complete. Engines still required installation. Certain control systems remained unfinished. But the aircraft was close. Very close. Unfortunately for Germany, Allied armies were closer. By April 1945, the sound of distant artillery could sometimes be heard from the factory. Workers understood exactly what it meant. The front was approaching. Every day reduced the likelihood that the aircraft would ever fly. Every day narrowed the window. The race was no longer against engineering challenges. It was against history itself. And history was winning. On April 14, 1945, elements of the United States Third Army entered the region. German resistance collapsed rapidly. Factories were overrun. Airfields captured. Research facilities seized. Among the discoveries awaiting American forces was something extraordinary. Hidden beneath camouflage netting sat the unfinished V-3, nearly complete, almost ready, and decades ahead of its time. The Americans immediately recognized its importance. Photographs were taken. Measurements recorded. Reports written. The aircraft was secured and added to the growing list of advanced German technologies destined for evaluation under a special Allied recovery effort known as Operation Lusty. The war was ending. The race for its secrets was just beginning. By the time Allied troops secured the unfinished Ho 229, the war in Europe was effectively over. Germany's defeat was no longer a possibility. It was a certainty. Factories lay in ruins. Transportation networks had collapsed. Fuel reserves were nearly exhausted. The industrial machine that had once threatened an entire continent was disintegrating beneath Allied pressure. And yet, sitting beneath camouflage netting at Gotha was an aircraft that seemed to belong to a different future entirely. The more engineers studied it, the stranger it appeared. Not because it used jet engines. Germany already possessed jet aircraft. Not because it was fast. Several late-war designs pursued extreme speed. What made the Ho 229 different was the way its designers had approached the problem itself. Most aircraft manufacturers of the era were asking how to build better airplanes. The Horten brothers were asking whether the airplane should look different altogether. The contrast becomes obvious when compared with Germany's other advanced wartime aircraft. The Messerschmitt Me 262 was a genuine technological breakthrough. As the world's first operational jet fighter, it demonstrated performance that shocked Allied pilots. Faster than any piston engine opponent, heavily armed, and capable of devastating bomber formations, the Me 262 represented the future of propulsion. Yet structurally, it remained familiar. It had a fuselage, a tail, conventional wings. Its jet engines were simply attached to an aircraft layout that aviation engineers already understood. The same was true of the Heinkel He-162. Despite its advanced engine, the aircraft still reflected traditional aerodynamic thinking. New propulsion, old architecture. The Ho 229 represented something fundamentally different. New propulsion combined with entirely new architecture. And layered on top of that was something else. A deliberate attempt to reduce detection. That distinction matters. Most technological progress occurs incrementally. An engine becomes more powerful. A gun becomes more accurate. A radar becomes more reliable. The underlying concept remains unchanged. The Ho 229 challenged the concept itself. The aircraft's shape was not simply unusual. It was intentional. Every curve, every contour, every surface existed because the Horten brothers believed conventional aircraft contained unnecessary structures that reduced efficiency. Their solution eliminated those structures wherever possible. The result was an aircraft that appeared radical in 1945 and remains striking today. Even modern observers often struggle to believe it originated during the Second World War. Across the Atlantic, a remarkably similar line of thought had emerged independently. American designer Jack Northrop had spent years exploring flying wing concepts through his own experimental programs. His aircraft shared many aerodynamic principles with the Horten designs. The resemblance was so strong that later historians often described the two efforts as parallel evolution. Two groups of engineers. Two continents. Two completely different industrial systems. Yet both arriving at many of the same conclusions. After the war, when American engineers gained access to German flying wing research, the similarities proved fascinating. Northrop reportedly viewed the Horten work not as imitation, but as confirmation. Evidence that another group of talented designers had followed the same logic and reached many of the same answers. What surprised him most was not the flying wing itself. It was the additional step, the radar reduction concept. That part had gone further than many American programs of the era. Assessing the true importance of the Ho 229 requires honesty. As a weapon of war, its impact was effectively zero. It never entered operational service. It never dropped bombs on Allied targets. It never intercepted a bomber. It never fought another aircraft. No battlefield was won because of it. No campaign was altered. No military outcome changed. Measured purely by wartime results, the Ho 229 accomplished nothing. That statement is entirely accurate and entirely misleading, because some technologies matter not for what they achieve immediately, but for what they demonstrate is possible. The Ho 229 belongs firmly in that category. Viewed through the lens of modern aerospace history, its significance becomes much larger. The aircraft demonstrated that radar observability could be influenced deliberately through shape and material selection. It demonstrated that flying wing configurations offered exceptional aerodynamic efficiency. It demonstrated that speed, range, and low observability could potentially coexist within a single design. Most importantly, it demonstrated these things in 1945, not 1965, not 1985, decades before stealth technology became a formal scientific discipline, decades before powerful computers could model radar reflections, decades before aerospace companies possessed the analytical tools considered essential today. The Horten brothers reached those conclusions largely through intuition, experimentation, and relentless engineering curiosity. That achievement remains extraordinary. The comparison most frequently made today is with the Northrop B-2 Spirit. At first glance, the resemblance is impossible to ignore. Both aircraft share the flying wing layout. Both prioritize aerodynamic cleanliness. Both seek to minimize radar visibility. Both derive performance from geometry as much as from propulsion. Of course, the differences are enormous. The B-2 employs advanced radar-absorbing materials produced through highly sophisticated industrial processes. Its flight controls rely on computers capable of making thousands of corrections every second. Its systems represent billions of dollars in research and development. The Ho 229 possessed none of those advantages. Its radar reduction efforts relied partly on charcoal mixed into wooden construction materials. Its designers worked with slide rules, intuition, and limited wartime resources. Yet the conceptual connection remains undeniable. The same fundamental logic appears in both aircraft. And that logic began taking shape in Germany during the darkest years of the war. There is something remarkable about that fact. The Horten brothers worked under conditions modern aerospace engineers would consider almost impossible. Materials were scarce. Fuel was scarce. Testing facilities were limited. Bombing raids interrupted production schedules constantly. Supply chains failed repeatedly. And still they produced an aircraft that anticipated design philosophies which would dominate military aviation decades later. They did so without advanced computers, without modern radar laboratories, without computational fluid dynamics, without the immense research budgets available to post-war superpowers. They worked largely with theory, experience, and determination. And somehow they arrived startlingly close to ideas that later became central to stealth aviation. When British intelligence teams gathered documents from German facilities in the final weeks of the war, they were not collecting magic. The blueprints alone could not create stealth aircraft. Technology still required decades of development. Industrial capabilities needed to evolve. Scientific understanding needed to mature. What those documents provided was something subtler. Validation. Proof that the idea worked. Proof that the shape mattered. Proof that radar observability could be influenced through design choices made from the very beginning of a project. For intelligence analysts and aerospace researchers alike, that realization was enormously valuable. The concept was no longer speculative. Someone had already built it. Today, the surviving V-3 airframe remains preserved in Maryland. Silent, incomplete, waiting. Visitors who eventually see it displayed in a museum will encounter more than a German experimental aircraft. They will encounter a crossroads in technological history, a machine that arrived too late to influence the war that created it, yet early enough to influence the future that followed. Raymar Horten lived until 1994, long enough to witness the age of stealth aircraft become reality. Long enough to see flying wings return as some of the most advanced military aircraft on Earth. No definitive record survives describing his reaction when photographs of the B-2 first appeared. Perhaps he admired it. Perhaps he felt vindicated. Perhaps he simply nodded. After all, he had spent most of his life arguing that the flying wing represented the logical endpoint of aircraft design. For a man who believed that for 60 years, there may have been very little left to say. The aircraft itself made the argument. It always had. And nearly half a century after the collapse of the Third Reich, the rest of the world finally began to catch up.